Right, so I made, technically, ChatGPT made this JavaScript application that is a neural net, and it seemed like a good idea to try to program it. So yeah, we'll just try to do that for a while. It may or may not lead to anything interesting, but so yeah, let me explain the visualization because it's a little janky. Not yeah, it's a little janky, but so we're in 3 dimensions, and each one of these little graphics is like a neuron, and we're feeding in 3-dimensional binary inputs, and we're actually going the flow is from top to bottom, because that's how ChatGPT did it, and that's fine. And so what we're visualizing is it's like these three. And yeah, the zooming is kind of bad. So these are 3 neurons or units. And the first hidden layer, right? So each input, right? There's like a 3-dimensional input, and it feeds into each one of these as a standard multi-layer perceptron. No, we don't use biases though. I don't have any biases. And so what we're visualizing in a single unit is what this unit does with each of the inputs, right? So each of these, I probably should have made these like different colors, but that's fine. So these are the 8 possible inputs in 3 dimensions, and it's visualizing what this parameter vector does, right? So like this input is the same as this parameter vector, so it has right, like it's sorting the inputs by Hamming distance to the parameter vector, which is analogous to computing a dot product in if you're using floating, like real value numbers. Right? And so yeah, so like this, right? And then you can click, and it animates. That's the cool thing. And right. So anyway, like that's the basic logic of what's happening here. Like we can click each weight, like where this is the parameter vector, and when you toggle a weight, it changes the Hamming distances to all of the possible inputs, and then like that updates the little graphic, right? Like so for instance, like this input is 1 away, and this input is 1 away, and this input, right? It's pretty straightforward, and right. And then what we're doing, what I thought I would try in this video, is the idea of like actually like trying to like solve so like I have these little, right, so the idea is that this blue input and this green input are arbitrary, and we're tracking them through the network. So if we just look at the blue guy, the blue guy is like 101, I guess, which is also, oh, I guess it's 010, yeah. Yeah, I mean, everything I say is like mod 2 or whatever, I don't know. Anyway, so it's 010. Yeah, like I'm visualizing 0 as a white, that's annoying. We'll just run with it though. Right, so 010, so it's highlighted as 010 in the first layer, because that's its representation feeding into the first layer. And then, if you look at these two units, right, like the purple line is the the decision boundary. So this unit outputs either a 0 or a 1. I don't actually know. And then the other two are 1 and 1. So if we then look at the blue, also ignore the circles. Those are, I think those are the activation. Yeah, those are the activations on the green. But so just ignore those. So anyway, going back to blue guy, this layer, the first layer, is mapping the blue guy from, like its input representation, which is 010, and then it's mapping it to like 011. So then if we look at the blue guy down here, okay, I got the colors inverted again, it's 100. Right, but so, right? So it's like it's a new representation, right? Because it's on the bottom of the decision boundary, then the top, and then the top. And so the bottom, I guess, corresponds to being black color on the next output. Yeah, so that's 100. And, and then this layer produces a new representation. It's like, for the blue, it's like top, bottom, top, which is actually its original representation, so I just mapped it back. And, yeah. And then, like, we're interpreting this unit, like, as the output, right? So that totally makes a lot of sense. So, right, so we can read off, like, from this input, so, like, ignoring these guys. So, like, this input, or like, our neural net, or output, is, like, it's classifying the green one as top, and the blue one as bottom. So, and I think it's the case. We can probably produce all, like, 4 possible classifications just by manipulating the weights here. Like, so, if we wanted blue to be on top, you just do that. And then, like, if you want them both to be on top, you don't do that. Okay. Maybe they can't both be on top. Oh yeah, they can't. They can't, because our neural net has mapped them to their negations of each other. White, black, white, black, white, black. And yeah, so yeah, they can't both be on the same side of the decision boundary, because they're negations. That's not actually true. I mean, like, you can have 2 negations, but anyway, yeah, so Right, okay, so like let's do that. Let's say keeping the same like training, problem set or like training set. We want the green input to be on the top, and the blue one. We want them both to be on the top, right? Okay, so like that's like the problem. We're going to try to solve, and yeah. So I mean that turns out to be solvable with a single unit, right? I mean, like, this unit is computing what we want, but nevertheless, we want it to be over here. And yeah, we have this we had like an idea of like you could do it in like a principled way by going backwards. I mean, I think it's like, I mean, like, in general, this is like, it'd be hard, but I think if you have, like if you have the ability to add units arbitrarily, I don't know if it's still, it'd be hard in that case. Probably is, but, yeah, yeah, okay, so like the principled way that we had in mind, was like to go backwards. So, right, so if we're saying like we want the blue and the green thingy to, on this unit, be above the purple line, yeah, you can like work backwards. You can say like, okay, yeah, that zooming sucks. You can say like, okay, this is my parameter vector, and so if it's going to be, right, I mean, like, this is explicitly telling you which inputs, and these are the previous layer inputs, not the raw inputs, right? Because like the representation changes. So it's saying like which, like, if you want a raw input to end up on the top of this decision boundary, that means like on this layer, the activations have to be one of these four, right? They either have to like match the parameter vector exactly, or they can be the parameter vector plus one of the indices being different. AKA you have to match 2 out of 3 of the indices of this parameter vector. So then you're just kind of like, okay, like if we take that parameter vector as fixed, then yeah, I mean that gives us explicit. I mean, for our problem set, right? Like we're already halfway there, because the blue input is being correctly classified. So all we have to do is figure out what's happening with the green guy. So the green guy is being mapped to like bottom, top, bottom, and it doesn't like that. This unit doesn't like black, white, black because it puts it on the bottom. So can we, but it looks like, if we take the green guy and we flip this middle bit to black on this layer, then the green guy will become this, and then they'll both be on the top, right? So let's see if we can do that. So we want to flip the middle bit for the green guy, which would be this unit, right? Ah, dang, right. So like this middle unit, we want to flip it from top to bottom. Now that looks like here, like this guy is pretty heavily, the green guy, you know, we want him to go under the purple line. And, but he's like maximally on the top. So I actually, you know, like I don't know if you can, also the question of, does it matter what's happening with the blue guy? Like if we flip him, if we flip his middle bit, you know, he'll go to all white, which would be bad. Yeah. So it's kind of like the problem is like, can you, the problem is, does there exist a parameter vector where these two representations, white, white, black, and black, white, white, are both distance, Hamming distance 2 or 3. Yeah. Now it turns out that problem is NP-hard. It's called, I mean, according to Wikipedia, you know, yeah, like given in binary strings, given a set of strings, dimension m, closest string problem seeks a new string, same dimension, such that the distance between the new string and all of the other strings is less than or equal to k, where d is the Hamming distance. The phrasing it here is optimization, k is as small as possible. We care about the decision problem version, which takes k as an input. So in our case, because we're computing majority, we care about k equals like n over 2. Or I guess like floor n over 2 or something. Question is whether there is a string, whether there exists a string with distance k of all the input strings. So yeah, like that's right. So even this basic problem is NP-hard. However, or actually it said it's NP-complete. I don't actually know the difference between NP-complete and NP-hard. I think NP-hard means it doesn't necessarily reduce to like a known NP problem, but it's, I don't know, it doesn't matter. I mean, you can probably look that up somewhere. Yeah, it doesn't matter. Okay. Right, so anyway, back to our thing here. We lost our train of thought. Although, you know, it's like, yeah. Yeah, it's kind of like, so like you're programming in this environment, you know, like if you're trying to program an MLP, you're programming in this environment where like every basic thing you might want to do, you know, you're like, is there a parameter vector that puts both green and blue on the bottom? That's our question. And I don't know, you know, I mean, I guess for 2, so, you know, we'll just kind of see what happens. If I click this guy, yeah, I mean, that might be good, though. Oh, there you go. Wow. Amazing. So, yeah, we have successfully put both of these on the bottom. I mean, you probably, like, people that are, like, smarter than me probably could have, like, pre-computed that, but I couldn't pre-compute that. So what happened? Yeah. Okay, actually, let's watch that, right? Because the green representation is now different, right? Like, we didn't touch this unit. It's still computing the exact same thing. But the green used to be this black, white, black thing. And now it's all black. Yeah, look at that. See? Like, it changes. The colors, they jump. Right? That's very cool. Yeah. So, yeah, I was trying to figure out, like, if there is, like, a reasonable way of, yeah, let's do 3 inputs. And then come up with, like, an arbitrary mapping. Orange? Is that a color? Alright. Okay, so let's just say I don't have any way of, like, let's say we want orange and green to be top and blue to be bottom. Solved. Like, we already solved it. Yeah. I need like a random number generator. Okay, I'll just write it. I don't know, I'll just come up with a random labeling, target labeling. Let's say bottom, top, bottom. Okay, that's like our target. That's not what's already happening, right? Yeah. Oh yeah, okay, so like it re-randomized and now oh yeah, okay, so like these, so for our first hidden layer, remember, like, we're going down, the inputs are like up here, not visualized, and they so yeah, these are all the exact same parameter vectors. Probability of that happening is 1 in 8 power 3. Is that 256? I don't know. Anyway, that just happened, so isn't that weird? Like, you would, I mean, is that even right though? Because I don't know math. Like, let me do the math on that. What did I just say? 8 power 3. Because, yeah, there's like 8 states, and then there's 3 of them, and they're all equal. So that's 8 power 3. So, anybody know what that is? It's 11. So, no, I'm just kidding. That's, how do you do it? Math.how. 8 power 3. 512. The probability of this happening is 1 in 512. Like, you would think that would never happen, but it just happened. That's amazing. So it's just, like, it shows you to never give up, you know? Because, like, if it, you know, like, 1 in 512 probability events happen every day in JavaScript programming. So, okay. Alright, so let's get back to whatever the hell we're doing. Okay, so we want blue to be on the bottom. So we want to be bottom. Whoops. So we want blue to be bottom. Green to be top. Orange to be bottom. Okay, so we want orange and blue to be bottom. Alright. and this is our output unit. And right, currently the first hidden layer collapses all of the units into, or all of the inputs into the same point, right? Because it's like top, 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 and that's top, I guess, is white. So like if I split that up, right, then all of a sudden, like, okay, green, we can distinguish green from, and I already forgot what I want to do. Oh, that's what we want. That's actually all we want. We just need to distinguish green from blue and orange. So, I guess maybe, yeah. And then we just want to put green on top. Okay, so in this layer, green is on top. And we just want to move orange down one. Okay, so if we go here, and we're like, I want to map orange to one of these bottom points. Like what is it currently close to? Yeah, I don't see an easy way of doing. What about this guy? This guy would put it. Ooh, I think that would work. Like, okay, so if we just drop this down, then this orange will go to here, right? Yeah, and then the green will stay there. Okay, so we just need to drop this guy down one. And I don't see how to do that, but... Oh, perfect. Oh, it went to a different one than I thought it would do. Nevertheless, I think that successfully computes a function. Because orange and blue are combined into orange. And so they're both mapped to this output, which is on the bottom. Great, that was easy. So, yeah, okay. Good. Okay, let's do... I don't know. Yeah, I'm not sure this is... I was thinking there would be a... Well, it's because... Yeah, well, I'll do like one more maybe. I need to get like some, I need to get like some random inputs. Yeah. Okay. We'll use AI for that. That way I don't have to think about it. Oh dang. Oh dang. Oh dang. Oh dang. Okay, doesn't matter. In JavaScript, a function to generate k-unique 01 vectors, all of length in. Please? Guys, you should always be polite to AI. seems way more complicated than I was expecting it to be. Right. Right, yeah, like it does like a set, then it splits it out. That's surprisingly complicated. You'd think there would be like an easy way of doing that. Okay. So, yeah, I need that real fast. Actually, I should have just generated. Well, that's fine. Doesn't matter. Okay. Actually, that's going to have to go up here, isn't it? Whoa. Okay, I don't need example usage. K and N. Formatting. I don't know why it doesn't copy paste formatting. I should ask it. I should ask AI. Okay, so then we want this to be yeah, I guess I want it to be like generate binary vectors. Let's do 4 of them. Dimension n, which I believe is already somewhere. And then we need another color. And I don't know. Yellow. Whoops. And then we need a target output. So, okay, plus 4. This is okay. Let's say training set size. Okay, do that. Do that, and then we're just going to print the target output, maybe. So generate, binary vector of length 1 n. Okay, this should all work perfectly. And I'm not seeing yellow happening. Why not? Oh, it broke. Why did it break? Seriously? Oh man. Does this need to say, is that the right? I guess that's right. So why is that not working? Generate binary vector. Math.round.